In this work, we talk about transferring kinesthetic demonstrations across diverse objects for manipulation planning. For any complex manipulation tasks such as pouring, our approach can extract the motion constraints from just a single demonstration and utilize the extracted constraints along with the geometric information of the task-related objects to generate motion plans for new instances of the task involving objects of different shapes and sizes as well as at different object poses. Since we are aiming to generate manipulation plans for objects of different geometries than those used in the demonstration, we need to consider three key aspects. Motion constraints corresponding to the task are satisfied, there is no collision between the task-related objects, and the desired task outcome is achieved. The first aspect of satisfying the motion constraints is achieved from our previous work, which this work is built upon. In our previous work, task space motion constraints are extracted from a single demonstration as a sequence of constant screw segments and then transferred to a new task instance to generate motion plans using screw linear interpolation. For the other two aspects, we must take the object geometries into account before transferring the motion constraints. Simply transferring the constant screw segments without considering the object geometry may result into collision, as happened while transferring the screws extracted from the pouring demonstration using a soup can to a new task instance involving a large box. In this work, we model objects as superelliptical cylinders with four parameters A, B, N, and height. By changing these parameters, our algorithm gets to work with a large set of geometrically different objects and thereby making it very robust. We assign a new motion transfer frame to critical points on the task related objects and call this the C frame. We first collect a single kinesthetic demonstration and then transfer it to the kinematic simulation to generate motion plans on a large number of geometrically diverse virtual objects using the method described in the paper. In the simulation, the red object represents the demonstration and the blue virtual object represents the new task instance. By changing the object parameters, we performed 3200 trials in simulation with different virtual objects of diverse geometries. For hardware experiments, we collected two kinesthetic demonstrations, one from a soup can to a bowl, and using this demonstration we performed 20 trials on various objects from the YCB benchmark, and they all turned out to be collision free. The second kinesthetic demonstration was from a cheese-it box to a flat plate. And finally, using this demonstration, we performed 20 more collision free trials on different objects from the same YCB benchmark.